Hello, Math 104 class. Elijah Marshall here, a part of Sexy Mathematics Productions, where we teach you the finest of mathematics. Now, today we're going to be talking about something called separable equations. Now, first of all, a separable equation falls under the category of a differential equation. And a differential equation is defined as an equation that contains an unknown function and one or more of its derivatives. Now, an example of that would be dy over dx is equal to y times x. You see you have the derivative and you have some function y or x, or a function of y and x inside one equation. This particular type would be considered a first order differential equation because you're only dealing with the first derivative. Now, it would be considered a second order differential equation if you had something that looked like second derivative, forget that dot, I'm sorry, over dx squared is equal to y times x. That would be considered a second order differential equation. Now, shall we look at some examples on how this is done? Forgive me for the paper, this is actually scratch paper. We gotta, reduce, reuse, and all that other good stuff, right? Before we go on to an example, separable equations are usually put inside the form dy dx is equal to some function of x times some function of y. Okay, before we move on, this is like the general form of a first order differential equation, which for separable equations, the ones that we're going to be dealing with are all going to be first order. Okay, now what makes separable equations so special, or a special case of differential equations, is that you can solve for the original function. We can find out what the original equation is for y in this sense. And I'm going to show you an example of that right now. If I can get some scratch paper. Okay. Now the first example I have is a pretty simple one where we have, let me make sure the camera's centered. We have x times y squared times y prime is equal to x plus 1. Now, initially what I like to do is I like to write this y prime out as dy dx. So I'm going to do x times y squared times dy dx is equal to x plus 1. Now, how do we know which variable we're solving for? The way we can figure this out is by looking at the derivative itself. And for our derivative, we have dy over dx, which says the derivative of y with respect to x, right? So because the derivative is of y, the original function we're going to be looking for is going to be in terms of y. So y is the variable we're going to be solving for. Now the whole idea here in the beginning is to separate the x's and the y's on different sides. Hope you guys don't mind, but I actually use bullet points to denote my next step. So what we're going to do right here is we're going to divide both sides by x so that we can separate the y's and the x's. So we're going to have y squared times dx is equal to x plus 1 divided by x. We're just divided both sides by x, okay? Now here's where things get kind of interesting. This dy dx right here can also be separated. That's what makes this a separable equation. We can multiply both sides by dx to get y squared dy is equal to x plus 1 over x dx. Now that we have our y terms and our x terms on one side, we're going to integrate both sides. Integral of y squared dy is equal to the integral of x plus 1 over x dx. Solving both integrals, we get the integral of y squared. It's going to be y cubed over 3 is equal to, now this can be rewritten, right? I'm going to actually do this step just so that you can see what's going on here. But because we have we have a variable and a constant, both being added and divided by a variable, we can separate this into two separate fractions. So we'll have the integral of x over x plus 1 over x dx, which is equal to y cubed over 3 is equal to, I shouldn't put equal, I'm going to put a little semicolon to denote that this is the next step. The integral of 1 plus 1 over x dx. Solving, I get y cubed over 3 is equal to, the integral of 1 is just x, and the integral of 1 over x is ln x. Now, because both of these are indefinite integrals, we're going to need our constant of integration, right? Technically, this is y cubed over 3 plus c, and this is going to be x plus c and ln x plus c once all integrals are evaluated. But what I'm going to do is I'm going to add the plus c over here on the right side, and this is going to account for the constants of all three integrals, okay? So the constant that I get from integrating this term, or from integrating, where's my original integral? This term, x over x and 1 over x, is all going to be held inside one constant c here, okay? Now, remember, the whole goal is we're trying to find the original function, which is going to be y, right? So we're going to solve for y by multiplying both sides by 3 and get y cubed is equal to 3x plus 3 ln x plus 3c, right? Taking the cube root of both sides, we're going to get y is equal to the cube root of 3x plus 3 ln x plus 3c. And this right here is our answer. That's exactly what we were looking for, right? The original function in terms of y. Now this right here is a simpler example. I'm going to show you guys another one that's a little bit more complicated. Well, not really more complicated, but it contains something a little special. In this example, we're going to have du over is equal to 2t plus secant squared t all over 2u. Now, this also contains something called an initial condition, which in this case it's u of 0 is equal to 5. Basically, the initial condition tells us that on the somewhere on the function, somewhere on the curve of u, where t is equal to, well, I guess where t is equal to 0 on the curve u, u is going to be equal to 5. So if I look where t is equal to 0, u is going to be equal to 5. This basically is going to give us a way to solve for our integration constant so that we don't have too many variables inside of our final answer, okay? You're going to see in a second how this is done. Now remember, what variable are we trying to solve for? Well, we look at the derivative. The derivative is of u with respect to time. So the original, or the function that we're trying to find, is going to be in terms of u, okay? Now to start this off, we're going to multiply both sides by 2u, just so that I get the u's on the left side and then the t's on the right side. So multiplying both sides by 2u, I'm going to get 2u du is equal to 2t plus secant squared t, right? Oops, almost forgot. This is actually du over dt. I jumped ahead a step. Now we're going to multiply both sides by dt so that we get the du and the u's on one side and the t's and the dt's on one side. So we're going to have 2u du is equal to 2t, should put that in parentheses, plus secant squared t dt. Now integrating both sides, we get 2u du is equal to the integral of 2t plus secant squared t dt. Evaluating both integrals, the integral of 2u is going to be 2u squared divided by 2. Integral of 2t is going to be 2t squared divided by 2. And what is the integral of secant squared t? It's going to be tangent. This is stuff, you know, I'm not going to lie, this got me earlier. I had to think about it. And what else am I done here? No. We're going to add the constant of integration. And remember, this constant of integration takes care of the constant from all three of these terms. Now, simplifying, I get u squared is equal to t squared plus tangent t plus c. Now this is where the initial condition comes in. Now it says when t is 0, u is equal to 5, right? So I'm going to use that to solve for my constant of integration here. So plugging in 5 for u, when t is 0, plus tangent 0 plus c, I get c is equal to 25. This takes care of the constant of integration. Now remember, originally what we're trying to do here is we're trying to solve explicitly for u, because that's what the derivative is of. Now that we have our constant, we can go back to this part, or this equation here, and we can solve explicitly for u. Now, taking the square root of both sides, I get u is equal to the square root of t squared plus tangent of t plus c, right? Plugging in our newly found constant of integration, before anything, I should do plus or minus here because it's square root. I get u is equal to plus or minus t squared plus tangent of t plus 25. I want to make sure this is under the radical. And this right here is our original, function of u. Now, let's just say, just being hypothetical here, say this was a negative 5, like in the original example out of the book. Then, to satisfy the initial condition, this wouldn't be plus or minus. This would be just negative, right? Because we have u, the function of u being equal to a negative number. So to satisfy the original initial condition, this would have to be negative. Well, now you know how to solve separable equations. This has been fun. You can find me at in real life. Just ask Professor Davis. Thank you for your time, and if you have any questions, like I said, find me in real life. Goodbye and good night.